Testing, can you hear me? Testing again. Testing one last time. Okay, this video is public now. So I'm going to be studying calculus again. Last stream, or not last stream, last calculus stream, I was studying the integral stuff. I was studying multiple integration and I read through these. I was studying vector calculus. I read through the entire chapter. I'm not good at it. Like the equations are not like cemented into my brain. So I'm going to revise it later, not this stream. I'm just going to finish reading calculus 3 and then I will relearn calculus 3, but more in depth. Anyways, let's change to full screen. Yeah. Okay, this is some other chapter. Vectors and space, vector calculus, second order differential equation, introduction. We have already studied the basics of differential equations, including separable first order equations. In this chapter, we'll go a little further and look at second order equations, which are equations containing second derivatives of the dependent variable. The solution methods we examine are different from those discussed earlier, and the solutions tend to involve trigonometric functions as well as exponential functions. Here we concentrate primarily on second order equations with constant coefficients. Okay, let's just go to the next chapter. Second order linear equation. Hold on. Second order linear equation. Okay, when working with differential equations, usually the goal is to find a solution. In other words, we want to find a function or functions that satisfies the differential equation. The technique we use to find these solutions varies depending on the form of the differential equation with which we are working. Second order differential equations have several important characteristics that can help us determine the solution method to use. In this section, we examine some of these characteristics and the associated terminology. Consider the second order differential equation. So only y is derivated twice, right? So x times y derivated twice, double derivative of y, plus 2x derivative of y, plus 5x cubed y equals 0. Notice that y and its derivatives appear in a relatively simple form. They are multiplied by functions of x but are not raised to any powers themselves, nor are they multiplied together. As discussed in Introduction to Differential Equations, first order equations with similar characteristics are said to be linear. The same is true of our second order equations. Also note that all the terms in this differential equation involve either y or one of its derivatives. There are no terms involving only functions of x. Equations like this, in which every term contains y or one of its derivatives, are called homogeneous. Not all differential equations are homogeneous. Consider the differential equation. We can divide both sides by x squared. The x squared term on the right side of the equal sign does not contain y or any of its derivatives. Therefore, this differential equation is non-homogeneous. A second order differential equation is linear if it can be written in the form so some function double derivative y plus some function derivative of y plus some function times y plus rx, where these are all real valued functions and a to x is not identically 0. If r what is equivalent to 0. In other words, if Rx is equal to 0 for every value of x, equation is said to be a homogeneous linear equation. Why is it represented like this? If R of x is equal to 0 for every value of x, can't they just say if R of x is equal to 0? If R of x is not equal to 0 for some values of x, the equation is said to be non-homogeneous linear equation. In linear differential equations, y and its derivatives can be raised only to the first power, and they may not be multiplied by one another. Terms involving y squared or root y derivative of y make the equation nonlinear. Functions of y and its derivatives, such as sine y or e to the power of derivative of y, are similarly prohibited in linear differential equation. It can only be in this form. Note that equations may not always be given in standard form. It can be helpful to rewrite them in that form to decide whether they are linear or whether a linear equation is homogeneous. Classify each of the following equations as linear or non-linear. If the equation is linear, determine whether it is homogeneous or non-homogeneous. So this here is linear non-homogeneous. This here is linear homogeneous. This here non-linear, linear non-homogeneous, linear non-homogeneous, linear non-homogeneous, non-linear, what? Non-linear, right? You can't have cos of y. Did I say linear or non-linear? This is non-linear because y squared. This is linear and homogeneous. This is non-linear. It's x because of x and x derivative. This is linear and non-homogeneous. C is D, linear, non-homogeneous. Non-linear. I think I made a mistake on this one. This is non-linear because sine of derivative y. F is linear. non-homogeneous. And then we have linear homogeneous. Wait, what? Yeah, -3 is alone, so linear non-homogeneous. We will see some techniques for solving specific types of differential equations. Before we get to that, however, let's get a feel of how solutions of linear differential equations behave. In many cases, solving differential equations depends on making educated guesses about what the solution might look like. Knowing how various types of solutions behave will be helpful. Consider the linear homogeneous differential equation. X squared double derivative of y minus x derivative of y minus 3y is equal to 0. Looking at this equation, notice that the coefficient functions are polynomials with high powers of x associated with higher order derivatives of y. Show that y is equal to x cubed is a solution to this differential equation. I mean, I can substitute in x cube, right? So 3x cube derivative of x cube is hold on. So example 7.2, I can just hold on a minute. There's something wrong with my board. Yeah, I can just substitute in the thing. Let me try again. Okay, this is working well. So x squared double derivative of y. Derivative y? Derivative with respect to what exactly? Plus x derivative y. And then minus 3y. Minus 3y. And it's minus xy. The derivative x cube is 3x squared. Double derivative of x cube is 3 times 2 is 6x. So we have 6x minus 3x squared minus 3x cube, which is equal to 6x cube. Sorry, this is x times. So becomes minus 6. I mean, that's proof that the solution works. How do we solve it? Although simply finding any solution to a differential equation is important, mathematicians and engineers often want to go beyond finding one solution to a differential equation to finding all solutions to a differential equation. In other words, we want to find a general solution just as with first order differential equations. A general solution gives the entire set of solutions to a differential equation. An important difference between the first order and second order is that at second order equations, we typically need to find two different solutions to the equations to find the general solution. If we find two solutions, then any linear combination of these solutions is also a solution. We state this fact as a following theorem. Superposition principle. If y1 and y2 are solutions to a linear homogeneous differential equation, then the function this where c1 and c2 are constant is also a solution. Given that e to the power of minus x and e to the power of 5x are solutions to this differential equation, show that for e to the power of minus x plus 5 plus e to the power of 5x is a solution. Don't we just substitute in the values? Yeah, that's what they expected us to do. Uh, Unfortunately, to find this general solution to a second order differential equation, it is not enough to find any two solutions and then combine them. Consider the differential equation. So we have this here. Both e to the power of minus 3t and 2e to the power of minus 3t are solutions. However, this won't work because C1 and C1, C2 and 2 can be taken out, right? So this expression does not account for all solutions. In particular, it fails to account for the function e to the power of minus 4t, which is also a solution to the differential equation. But that's because this here is a multiple of this. A set of functions is said to be linearly dependent if there are constants, c1 to n, not all zeros, such that this is equal to 0 for all x over the interval of interest. A set of function that is not linearly dependent is said to be linearly independent. In this chapter, we usually test sets of only two functions for linear independence, which allows us to simplify this definition. From a practical perspective, we see that two functions are linearly dependent if either one of them is identically zero, or if there are constant multiples of each other. First, we show that if the functions meet the conditions given previously, then they are linearly dependent. If one of the functions is identically zero, say f2x, then choose c1 is equal to 0 and c2 is equal to 1, then the condition for the linear dependence is satisfied. If on the other hand, neither f1 nor f2 is identically 0, but f1 is equal to c times f2 for some constant c, then choose c1 is equal to 1 over c and c2 is equal to minus 1, and again the condition is satisfied. Determine whether the following pairs of functions are linearly dependent or linearly independent. So these are dependent. No. Would it matter if I change the input? No, right? If I multiply it with e to the power of minus 6, then I get e to the power of minus 3x, right? So these are independent. These are dependent. These are independent, dependent. Dependent, independent. Last one is independent. And what about this? E3x equal to don't get confused by the fact that exponents are constant multiples of each other with two exponential functions. Unless the exponentials are equal, the functions are linearly independent. Hold on a minute. Hold on a minute. g of x. That doesn't make any sense. Um, Actually, that does make sense. Or maybe not. Actually, yeah, it does make sense. If y1 and y2 are linearly independent solutions to a second order linear homogeneous differential equation, then the general solution is given by this. The C1 and C2 are constants. When we say a family of functions is the general solution to a differential equation, we mean that 1, every expression of that formula is a solution, and 2, every solution to the differential equation can be written in that form, which makes this theorem extremely powerful. If we can find two linearly independent solutions to a differential equation, we have effectively found all solutions to the differential equation. Quite a remarkable statement. Proof of this theorem is beyond the scope of this text. Okay, after I'm done with this book, I want to read some other book that's more proof focused. Um, when we every expression of that form is a solution. Every solution to the differential equation can be written in that form. If y1 is this, y2 is this, are solutions to this, what is the general solution? We just write c1 y1 plus c2 y2, right? So c1 this plus c2 this. But the thing is, they want us to find a general solution. Hold on. Okay, let me think about this. Example 7.5. Y1 is equal to E3t. Y2 is equal to E minus 3t. Are solutions to um are solutions to this. They're saying the general solution is C1 plus E minus 3t. They're saying this is the general solution. So the derivative is, wait, isn't minus 9? Yeah, it is. The derivative of this is derivative of this. No, respect to t. Respect to t. Um, Derivative of this stays the same. Derivative of 3t is just 3. plus and the same thing but with minus. This has to be C2. Now what do I do with this? Do I bring the double derivative? 3 and C1 are constant and the same thing. 3 times 3 is 9. Minus 3, 9. Now I don't understand what to do with this. Do I just put this over here? This is the double derivative. And then I do minus 9 multiplied with these two. I didn't go anywhere with this. Yeah, this is just 0. Nothing happened. Um, I need a better solution. Oh, wait, do the coefficient have to be a particular number or can they just be anything? Where is the theorem for this? Where C1 and C2 are constants, also a solution. But they can be any constants. It doesn't matter what constants they are. Because if I replace C1 and C2 here with any random number, this entire function will still work. This entire thing will still work. Now that we have a better feel for linear differential equations, we are going to concentrate on solving second order equations of the form a divided by y plus b divided by y plus cy is equal to 0. Since all coefficients are constants, the solutions are probably going to be functions with derivatives that are constant multiples of themselves. We need all terms to cancel out, and if taking a derivative introduces a term that is not a multiple constant of the original function, it is difficult to see how that term cancels out. Exponential functions are derivatives that are constant multiples of the original function. So let's see what happens when we try a solution of the form e to the power of lambda x. Lambda is some constant. So y is equal to e to the power of lambda x. Derivative is this. Double derivative is this. So this, we do the thing and we end up with this. And then since this is equal to 0, this or this has to be 0, right? Since e to the power of alpha x is never 0, this expression can be equal to 0 if for all x can be equal to 0 for all x, only if this is, so this part has to be 0. We can call this characteristic equation of the differential equation. The characteristic equation of the differential equation, this is this, but now we are tasked with finding this, right? Oh, we can just solve for a lambda using the quadratic equation. 1 distinct real roots, a single repeated root, 3 complex conjugate root. If the characteristic equation has distinct real roots, then E lambda 1x and E lambda 2x are linearly independent solutions to example 7.1. And the general solution is given by this. For example, the differential equation has the associated characteristic equation. This factors into this, which has roots -2 and -7. Therefore, e to the power of -2 and e to the power of -7 is the general solution. Single repeated root. Things are a little more complicated if the characteristic equation has a repeated root, lambda. In this case, we know E lambda x is a solution to equation 7.1, but there's only one solution, and we need two linearly independent solutions to determine the general solution. You might be tempted to try the function of the form k e lambda x, where k is some constant, but it would not be linearly independent of e to the power of lambda x. Therefore, let's try x e lambda x as a second solution. First, note by the quadratic formula, we have this. But lambda is a repeated root. So b square minus 4ac is equal to 0. Hold on. Single repeated real root. Why do they call it repeated? If it's a single root, then I understand this. And lambda is equal to minus b over 2a. Thus, if y is equal to x e to the power of lambda x, we have derivative of y. Wait, hold on. Up here, when they said y is equal to e to the power of lambda x, we ended up over here, right? We ended up over here, and this is how we got this, and this is how we got that lambda is equal to this. But then, if y is equal to x e to the power of lambda x, then this would be e to the power of lambda x. And x times e to the power of lambda x would not be 0, because x is the input, and we are looking for non-zero inputs. Okay. First, note that by the quadratic formula, we have this. Then we have derivative of y. If this, we have this, and double derivative is this. We take this out. Oh no, wait, I got it wrong. If it's this, then we have this. We take this out. Y 0 over here. A lambda square. Substituting into equation 7.1. Okay, I don't understand why they're doing that 0. Why? Okay, why is this 0? And then we have plus 2a lambda plus b. I understand why they did this is this part is equal to 0 in this specific case when y is equal to e to the power of lambda x. But over here, when we have y is equal to x times e to the power of lambda x, then this argument doesn't work. This entire thing has to be 0. This shows that x e to the power of lambda x is a solution to equation 7.1. Since e to the power of lambda x and x e to the power of lambda x are linearly independent, the characteristic equation has a repeated root lambda. General solution is given by this. Okay, I understood this. Therefore, let's try this as a second solution. First, not that by the quadratic formula. There are two solutions, not in the form of this. One solution is this. One solution is in this form. There is another solution in this form. So if this is a solution, then lambda would have to be written like, okay, that makes sense now. There are two solutions, this form and this form. Since this is a solution, this has to be 0. Complex conjugate roots. Third case we must consider is when b square minus 4ac is less than 0. In this case, when we apply the quadratic formula, we are taking the square root of a negative number, which we use as the of the negative number. We must use the imaginary number I to find the roots, which take the form lambda 1 is equal to alpha plus beta I, and lambda 2 is equal to alpha minus beta I. The complex number is called the conjugate. Okay, the complex number alpha plus beta I is called the conjugate of alpha minus beta I. Thus, we see that b square minus 4ac is less than 0. When this is the case, the roots of our characteristic equation are always complex conjugates. This creates a little bit of problem for us if we follow the same process we used for distinct real roots. Using the roots of characteristic equation as the coefficient in the exponents of exponential function, we get the functions this and this as a solution. However, there are problems with this approach. First, these functions take on complex values, and a complete discussion of such functions is beyond the scope of this text. Second, even if we are compatible with complex value functions, in this course we do not address the idea of derivative for such functions. So if possible, we would like to find the We would like to find two linearly independent real value solutions to this differential equation. For purposes of this development, we are going to manipulate and differentiate the function as they were real valued functions. For these practical functions, this approach is valid mathematically. But be aware there are instances when complex value functions do not follow the same rules as real valued functions. Those if you're interested in more in-depth discussion on complex value functions should consult a complex analysis text. Based on the roots alpha plus minus beta I of the characteristic equation, the functions these two are linearly independent solutions of the differential equation to the differential equation. And the general solution is given by this. Using some smart choices for C1 and C2 and a little bit of algebraic manipulation, we can find two linearly independent real value solutions to equation 1.7 and express our general solution in those terms. We encountered exponential functions with complex exponents earlier. One of the key tools we used to express these exponential functions in terms of sines and cosines was Euler's formula, which tells us that e to the power of I theta is cos theta plus I sine theta. Going back to the general solution we have. So this, maybe are splitting up these two. You're taking E alpha x out. And then cosine. Cos minus x is equal to cos x. So cos beta x, cos minus beta x will turn into cos beta x. And then since this is minus, sine minus beta x will turn into minus sine beta x, right? So C1 plus this, C1 times this plus C2 times C1 times the, okay, I can't even highlight properly. Never mind. C1 times cos plus C1 times I sine and then plus C2 cos and then minus C2 I sine, right? And then we end up with this. Now, if you choose C1 is equal to C2, which is equal to half, second term is 0, we get second term is 0. Half, this becomes 1, this becomes 0, and then we get this. As a real value solution for equation 7.1. Similarly, if we choose C1 is equal to minus I over 2 and C2 is equal to I over 2, first term is 0 and we get this as second linearly independent real value solution. Based on this, we see if the characteristic equation has complex conjugate roots alpha plus minus beta I, then the general solution to equation 7.1 is given by this. Oh my gosh, there's so much to memorize. Distinct real roots. A repeated real root. Complex conjugate roots. Example 7.6. Copy. Getting rid of all this. Delete. 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 Paste. Example 7.6. We have A. So if we have something like this, if we have this, then the solution is given distinct real roots, repeated real root, complex conjugate roots. Okay. 1, 3, minus 4. So 1, 3, minus 4, we write lambda. Yeah, 1 times lambda square plus 3 lambda minus 4 is equal to 0. And then lambda is equal to minus p plus minus p square minus 4 times a times c. I'll just write plus 16 over 2a. 16 plus 9 is 25. Then minus 3 plus 5 over 2 minus 3 minus 5 over 2. 5 minus 3 is 2. 2 over 2 is 1. Minus 5 minus 3 is minus 8. We have minus 4. So the solution is this. Let me see. Minus 4 and this. Let me see. C1, C2. I have to write C1 and C2, right? What this work? Yeah, let's see just the first one. Okay, this is correct. So let's try B. We have lambda square again plus 6 lambda plus 13 minus b square 36 minus 4 times a times c over 2a. 4 times 13, 36 minus 4 times 13, minus 16. Minus 16. So this is equal to minus 3 plus minus 4i plus minus 2i. Now we have a complex conjugate situation. Then the equation is e to the power of alpha x. Okay. Y is equal to e to the power of alpha x c1 cos beta x plus c2 sine beta x, c2 sine beta x. 2t, it's t, not x. Yeah, who cares? 2t sine t minus 3. Do I have to write x on top? Yeah, I do. C 1, 2, 1. 1, 2, 1. Lambda is equal to minus p plus minus p square minus 4 ac over 2a. This is 0 minus 2, which is 1. So minus x, hold on, c1 and then plus c2. Let's see that if that's the answer. ABC. Yes, that is the answer. Now, question D. Question D. What is it? 1 minus 5, 0. 1 minus 5, 0. Lambda is equal to minus p plus minus p square minus 4 times AC over 2a. And 5 minus 5 is 0. 5 plus 5 is 10, and we are left with 5. It's a single solution. CD, C1. Step 4. C2 e to the power of 5. Hold on. No, even 0 itself is a solution. Yeah. 0 itself is a solution. So we do have two, it's a case of two solution, not one solution. The second solution is e to the power of 0. Oh yeah, okay. Then we have, sure. Question E. 1 minus 16. Sorry, 1, 0 minus 16. 1, 0 minus 16. Lambda is minus p plus minus p square minus 4 times AC over 2a. What is 4 times 16? 64. So that's root 8, right? Sorry. 8 over 2 is 4. Then we have minus 4. Plus 4x. A, B, C, D, E, F. Let me check E. 4 minus 4. 1, 0, positive 16. 1, 0, positive 16. Okay. Minus 4 times A times C over 2A is equal to yeah, minus 4i 4i plus minus 4i. E to the power of alpha x, but there is no alpha, so it's just 1. C1 cos beta, but the thing is, if I put minus 4, it's not going to make a difference. Sine like that, right? Sine 4x. I should write plus minus 4. I think it will be easier to understand as a single beta. Okay, this is done. Initial value problems and boundary value problems. So far, we have been finding general solutions to differential equations. However, differential equations are often used to describe physical systems, and the person studying that physical system usually knows something about the state of that system at one or more points in time. For example, if a constant coefficient differential equation is representing how far a motorcycle shock absorber is compressed, you might know that the rider is still sitting on his motorcycle at the start of a race at t is equal to time is equal to time t is equal to t naught. This means the system is at equilibrium, so y t naught is equal to 0, and the compression of the shock absorber is not changing, so derivative of y is 0. With these two initial conditions, the general solution to the differential equation, we can find the specific solution to the differential equation that satisfies both initial conditions. This process is known as solving an initial value problem. Note that second order equations have two arbitrary constants and the general solution. Therefore, we require two initial conditions to find the solution to the initial value problem. Sometimes we know the condition of a system at two different times. For example, we might know why T naught is Y naught and why T1 is Y1. These conditions are called boundary conditions, and finding the solution to the differential equation that satisfies the boundary condition is called solving a boundary value problem. Mathematicians, scientists, and engineers are interested in understanding the conditions under which an initial value problem or boundary value problem has a unique solution. Although a complete treatment of this topic is beyond the scope of this text, it is useful to know within the context of this constant coefficient second order equations, initial value problems are guaranteed to have a unique solution as long as two initial conditions are provided. Boundary value problems, however, are not as well behaved. Even when two boundary conditions are known, we may encounter boundary value problems with unique solutions. Many solutions or no solution at all. Solve the following initial value problem. So y0 is 1, derivative of y at 0 is negative 9. Example 7.7. Double derivative of y plus 3 minus 4y is 0. So 1, 3 minus 4, 1, 3 minus 4, minus b plus minus b square minus 4 ac. This is 25. Oh, this is 5. And then 2, 1, and then minus 4. This is because of minus 8. And so the solution is e to the power of x, sorry, c1 e to the power of x plus c2 e to the power of minus 4x. I think I did this before. Minus 4 and x. And they said y0 is 1. Negative 9. It is 1. Derivative of y is 9. So 1. y0 is 1. So z1 is equal to 0, 0 plus c2. And then the derivative of y is equal to, this doesn't change. And then this becomes minus 4 c2. And then add 0. So this is 0, this is 0, add 0, this is minus 9, minus 4 c2. So we have these two equations. Plus 4 c2 is equal to c1. So going back here, plus C2. We bring 9 to the other side. 5C2, C2 is 2. And then, since this is 2, this is negative 1. So we have minus e to the power of x plus 2, e to the power of minus 4x. Okay. Solving a boundary value problem. Initial value. Sometimes we know the condition of the two system at two different times. For example, these are called boundary conditions. Finding the solution to a differential equation that satisfies the boundary condition is called solving a boundary value problem. Let's try this boundary value problem, 7.10. And then I will end the stream. Example 7.10. Let me just take a picture. Copy. And let me paste it here. And then let me delete this because it takes up space. Okay. We solved this on the general solution. This, if possible, solve the boundary value problem if the boundary conditions are the following. So A, y 0, 0, 0. Cos 0 is 1. Sine 0. This is 0, so 0. Cos 0 is 1. Sine 0 is 0. So C1 is 0. Pi over 4. If C1 is 0, then I don't need to write this, right? I just need to write C2. Sine pi. Sine pi is what? No, wait. C2 also has to be 0. So yt is 0. For all values. Hold on. Sine. If I have it what? Sine pi is 0. Sine pi itself is 0, but we don't know anything about C2. So this, we can't solve the equation with these conditions, right? Thus, this is a solution for any value of C2. Hold on, cos 0. Cos. I don't know why I was so confused. Okay, anyways, B, we have Y, 1, C1 cos 4 plus C2, this cos t, right? Plus C2 sin t. That's not Y. Why does Y 0? 0, 0 is 1. This is 1. This is 0. C1 is, this is 1. This is 0. So C1 is just 1. So by pi over 8, pi over 8 is equal to C1 cos pi over 2 plus C2 sine pi over 2. Cos pi over 2 is 0. This is 0. Sine pi over 2 is positive 1. So C2 is 0. C1 is 1, C2 is 0. So solution is this. Now for question C. Y pi over 8 well, it's just this, right? I'll just copy this. And then what is this? 0. This is 0. So y over 8 is 0. Y 3 pi over 8. C1 cos 3 over 2 pi plus C2 sine 3 over 2 pi. Three over 2 pi. Okay, this is 0. This part is 0. We already established C2 is equal to 0. C2 is 0. What did they say? This is equal to 2. This doesn't lead us anywhere. This is 0. But C2 is 0. You have a contradiction. We cannot have 0. So this boundary value problem has no solution. And why did they say minus 2? Positive 3 over 3 over 8, but it's times 4, right? So 4. So this 8 becomes a 2. Oh, maybe sine. Yeah, because of sine. Okay, I will end my stream here then. I did learn something, but I don't like how it says that the proof is beyond this text. Because like a lack of proof would really bother me. So I need an open source book that's proof heavy. after reading this entire calculus book and finally finishing calculus volume 3, I'll start learning I'll start learning real analysis from the beginning with all the proofs. Okay, I will end the stream here and yeah, I will see you guys next time. Bye.